All right, so how are you doing?
Pretty good, pretty good.
Okay, okay.
Can you see my screen now?
Yeah.
Oh, okay. I have like four questions. So the first question is probably a shorter one. So, so when we were going over um, the cycle of a node value session,
Hmm?
there was one code I didn't understand. So here, as you can see, zz underscore v, z
Hmm.
underscore v. So
Hmm.
what does the underscore v mean?
So basically, we are running session, right? Session dot run on the right hand side, right?
Mm-hmm. Mm-hmm.
And what we're doing there is we are passing three inputs, right?
Mm-hmm.
Z, 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 and Y. These are the five nodes, three nodes. And those three nodes, when you run them, they will return three values, right?
Mm-hmm.
Those three values we are assigning to new variables.
Oh, just assign them over there. Okay, I see.
Okay.
Okay.
Yeah,
Okay.
that's
Also, so you run S, and ZZ would be
one of the
ZZ square. Okay. Okay. Got it. Got it. Okay. Understand.
okay,
Thanks.
okay.
Okay. So the next question is we so the linear regression. So we use the housing price as an example of doing the linear regression. So how do we
Hmm.
know the housing price is a linear equation of each criteria? Is it just an assumption so that we can do the?
It's an assumption.
It's just
It's an
assumption. Okay.
assumption.
Okay. So linear regression can only be used to resolve linear problems. If the
Yeah,
relationship between input and output are not linear, then we can't use linear regression.
yeah, that's
I
right.
see. I see. I
Also,
see.
see from the other perspective that actually we use mostly the linear regression, even for the nonlinear cases. All
Mm-hmm.
right. Imagine, do you mind? I'll just share my screen. It's a very good question, so I'd like to let me first of all close the unnecessary documents. All right. Okay, let me clear up my screen and then I can share the screen. It's a very good question. So the other part to the story is that what we do is we convert most of the problem into linear problems. Okay.
Mm-hmm.
Now imagine this that okay, let me. Okay. So what we generally do is we call them polynomial features. So we convert a nonlinear problem into a linear one, and that solves. You know, imagine that this is your y-axis and this is your x-axis, right?
Mm-hmm.
And imagine that the data was something like this. Okay.
Mm-hmm.
So for value x, imagine this is 1 and this is say okay, how should I say, all right, let me just, so imagine the equation of this one. I don't know right now. Okay, it is, let's say, 4x plus 3. Okay,
Mm-hmm.
something like this. So for x equals 1, it is a, let's say this is 7, right? Or how should it be? It should be something like, say, 7x minus, let's say, okay, so at x something, the y has to be minimum, something like this. Okay. So what we generally do is one of the chapters I discussed earlier. So what we do is we convert this into the linear function. Okay. We come up with the polynomial features and uh, I'll take some time to come up with a good example. This
Mm-hmm.
is y, this is x. Imagine that this is for 1, this is 1,
Mm-hmm.
and for -1 also this is 1, for
Mm-hmm.
-2 is 4, and for 0 this is 0, and so on, right? So
Mm-hmm.
this is something like this kind of a parabola.
Mm-hmm.
Okay.
Yep.
Now, what happens is that we can't really fit a line into this, right? We can't
Right.
really do that. So what we do is we convert these into polynomial features. Okay.
Um,
Imagine that we add a term here. Let's call it x1. Okay.
mm-hmm.
X1 is a square of x. Okay. We put like 1, 1, 4, 0, right?
Mm-hmm. Mm-hmm.
And let's say we add one more term here, called this is x square, and let's say this is third feature we are adding. This is called, let's say, x cube. Okay, and we got some value for it. Now we got we got like three features: x, x1, and x3, and we got y, right? So we'll say that okay, y is a linear function of axis. So we'll say w naught plus w1x plus w2x1 plus w3x3. Correct? Now, what will happen when we are trying to find this plane? So this is not a line, this is a hyperplane. This
Mm-hmm.
hyperplane has some slope in x direct well, in one dimension, some slope in another, some slope in another, and this is how far it is from the center. Got it?
Mm,
Okay.
no.
Okay, let me go back. Let me go
Uh,
back. So till this point you are clear, right?
yeah, I know the two extra column there. I understand that part. Why is y equal to this w1, w2?
Yeah, imagine that now we're given this data, we added features to it. Okay, this is called we basically are creating more features. Okay, so the point I'm trying to make is that you can solve a wide variety of problems with the linear regression. Okay,
Mm-hmm.
even the polynomial regression is actually linear regression. All we do is we add these features,
Mm-hmm.
okay, and then we express it as we think of it like through this we'll do the linear regression. And what does it mean by linear regression? Coming up with these weights such that when we multiply these weights with these things, we should get the correct y. Correct?
Yep.
That's the linear regression.
Yep.
So now we are expressing y as w naught, w1x, right? These are the
Mm-hmm.
weights that we want to find out. These are the weights that we want to find out, so that uh, when we put these values from this our known data set, the
Mm-hmm.
y that we predict should be really equal to the very close to the actual, right?
Oh. Oh.
Okay. Now,
Um.
okay, go ahead. Your question.
Oh yeah. Hmm. I didn't really understand why the math happens to match, but I think yeah, it kind of makes sense. Uh,
Okay.
so basically, if the more column we add,
Yeah.
the more accurate this approximation will be. Is it correct?
Kind of yes. So what
Uh,
will kind of yes. What will happen is there are like the same column were repeated, right? So what will
mhm,
happen is that this weight for which we are having the normal x, they'll be like really tiny after a lot of discovery, a lot of gradient descent. They'll become like zero. Okay. And this one, which is a square of this one, this will become really big. Okay, this
mhm,
will be really bigger than zero, and
mhm.
this will other factors, they will also slowly, because of gradient descent, try and error, the w3 will also go down to zero.
Oh, I see.
Okay.
Okay, okay. I think that makes a lot more sense now. Okay.
Okay, so
Hmm.
now because of gradient descent, this automatically will keep on going down, and this will keep on going up, and this will also go down, and eventually we will end up with our equation like y equals x square.
Oh, I see.
All right.
Cool. That's smart.
Yeah.
Cool.
The other
Uh,
part, other way you can think of it, we are coming up with a plane
mhm,
which is kind of slanting only in this direction, which has
mhm,
some slope here, but it's flat with respect to these. Okay, that's
mhm.
what will happen eventually here. So yeah,
Oh, I see, I see.
all
Cool,
right.
thank you.
Okay,
Okay,
all right.
awesome. Cool. So my next question is about the equation of the gradient
Uh,
descent. So I'm going to share my screen again.
yes, go ahead.
So, so this equation, as you can see on the left, I don't really understand this equation. So first of all, what is MSE?
Mean square error.
Sorry, what is that?
Mean square error.
Mean square error. Okay, I'm just gonna type that.
Okay.
Mean square
I'll also update the slides. Huh? That'll
error.
be better.
Okay, so an M is, so in this equation, what is M? M,
Mm,
like O2 over M, is M,
M is total number of instances, rows.
uh, number of instance, okay, number of rows, instance, okay. Um, so, so in this equation, I can see this, like inverse triangle, so, and
It,
it's equal to the thing in the middle. What is the thing in the middle? Do we like aggregate them, or
it's
would we
you can think of it like an array of values.
array of values? So it's array of square
Mean square
of
errors.
mean square errors. So say we every time we change a little bit, then the
Yeah,
rate of change
yeah,
uh, times the difference square of the error.
yeah,
Oh, okay, I see. So that's an array of rate of change
yeah.
times error square. And on the right hand side, it's
Hmm.
2 over m. X is what is x again? It's a metric.
Again, yeah, it's you can think of it like a big array of values, and that's how you can think of. Okay, should I just show you what it means? That'll
For
be
sure, for sure.
okay. So let me go back to sharing my screen. So I'll just do a quick, probably. Okay, so all right. Imagine that we are given some data sets here. Let's be very clear with the nomenclature. Okay, so this is our label, and this big thing is our capital X. Okay,
Mm-hmm.
this one has got rows, and this is our label, right?
Mm-hmm.
For this has got features, right?
Mm-hmm.
It is, and we will call them n number of features, right?
Mm-hmm.
And this is called m.
Oh,
M
m.
means instances, and n is the number of columns, right?
Okay. Okay.
The
I see.
features. Yeah.
Mm-hmm.
The more data we have, the m keeps on increasing, right?
Mm-hmm.
And yeah, overall accuracy keeps on improving the more data we have. And this is the label. For the data that we have, the training data, we generally have these values available with us. And when we don't, and the objective of the exercise is come up with the model that can predict the y given x. Okay,
Mm-hmm.
this is called small x. We call it x1, x2, and like that. This is how
Mm-hmm.
we generally put nomenclature at the top, like so. As a suffix. Similarly here, y1, y2. I hope this is clear to you.
Yeah, I think
So
that makes sense. Yeah.
based on this, we want to do the prediction. Perfect.
Okay. I see. I
Now,
see.
now what we say is that imagine we came up with some w's, right?
Mm-hmm.
We came up with, let's say, y equals w naught. plus W1x. Here again, I'm using this, okay? But notice this is at the bottom of this, okay?
Mhm.
X2, this is one column, this is another column,
Mhm.
this is another column, this is
Mhm.
another column, right? So we are saying the y, the outcome is equals to W naught, W1,
Mhm.
X1, right? Also notice that if we have to really be correct, we have to say something like this. Y1 equals W naught plus W1 and X1 at the top. We are talking about the first row, okay?
Mhm.
And W2, X2 and something like this, right?
I see. I see. Mhm.
This is clear, right?
Yeah.
Now, this is a value, this is a single value, this is a single value, this is a single value.
Mhm.
Similarly, we'll have to write many equations, correct?
Mhm. Yeah.
Like that. Now, this will become really pain to do all of this. So instead,
Mhm.
if we could, ideally, we would be writing a for loop or going over values, right?
Mhm.
But to express the same thing as vectors, we could either do something like, okay, y1 equals w naught, right? Plus
Mhm.
we put this as w1, w2, right?
Mhm.
Dot product with x1 and x2.
Oh,
Okay.
so it's just a simple way to write all those rows.
Right, right. So this is basically a simple way to just write it that way.
Mm,
This single one, okay? This single one, okay? Right now
I
we just
see.
are trying to express this single one where all of these are values. Now, if you make it a little better, right? If we could just put one more things in this, so a better way would be like if we put 1 1 and we
Mhm.
say x1 1 instead of this way because this looks really ugly if you see although we are able
Mhm.
to express it in a vector, but this looks really ugly. Now this looks really easy to w naught, w1 and w2, right? uh,
Mhm.
and so how should I say? I kind of made a mistake here. It is going to be x2 dash. Okay, so this is 1 x1 1 x2 1, right? First row we took. We are
Mhm.
only talking about these first two columns. I'm not going with beyond this. Okay, we are just talking about
Mhm.
this. So same equation. This can be written nicely here. So 1 gets multiplied with W naught, x1 get multiplied with the W1, and
Mhm.
x2 get multiplied with this. Okay.
I see. I see.
So we just added one extra in the brackets. Now the whole equation becomes really easy. Now,
Oh, I see.
further we could say that, okay, there will be so many such equations, okay, and we'll be having like this. So this actually becomes like y equals capital X,
Mhm.
including bias. We call it capital X, including bias. We added one more one here, right? Like this. So whatever
Yeah.
values were there in this, we took exactly that way and put extra one there and put that like that. This. Okay. Makes sense.
Uh, W W is V1, V naught V1. W. Oh, no, wait, that's
Mm.
N.
Mhm.
Oh, okay.
Okay. So imagine this now. We could actually stack up all the rows. We could say 1 x1 1 first row, then
Mhm.
second row will be second row from here, and
Okay.
we can express the whole matrix like this
Mhm.
y is a function of all of
Oh,
this multiplied with weights.
okay.
So that's the expression. I hope this is clear. No.
Yeah, yeah, I get it. I get it now. Yeah, I
Okay.
see.
Now, if we move ahead, so what will be if we, let's say, what will be our, this is our this is our predicted value. Okay, this is not
Mhm.
really actual value. Okay, actual value would be different because not everything is a linear regression, or it's
Mhm.
not perfect linear regression. So here this is our predicted value, right?
Mhm.
And initially all these weights will be random, and then we'll start tweaking them. Right now we don't know their values, so we want to figure out those values. Now first thing we're going to do is we are going to compute the error, right?
Mhm.
How much is the error between this and this? Okay,
Mm-hmm.
so that is called the error, right, between these two.
Mm-hmm.
And this is, let's say, this is going to be the error between this and this is how much? Um, Whatever we have done here, okay, we call, let's say, we express this as, let's call it like x dot w, okay?
Okay.
If the whole equation, we could say x along with bias, each row along with bias, right, multiplied by weights. This thing, I'm writing it like this, okay? And, ouch, and subtracted by actual value, whatever is it was there, right? And then we square it, correct?
So when you say X with bias, what do you mean by
We added
with bias?
we added one more here. That's all.
Oh, you add one
One
more
here.
thing on the at the beginning. That's what you call bias.
Yeah,
I
yeah.
see. I see.
Now this is error. So we came up with some weights, and we came up with so these weights led to some value, right? And the same thing we'll do here also, correct? Same thing
Mm-hmm.
we'll do here also. So this one we will write for let's call it for first row, and then we'll say, okay, the average value is going to be, we do it for the second row. We took the second row, right? Put the bias on top, like added one more here,
Mm-hmm.
multiplied with weights. This is this equation minus the actual y, right? So
Mm-hmm.
for this, we basically put the weights, multiplied the weights with each of these values, summed up with W naught, and subtracted this, right? We did this second one. So what we're trying to do is, whatever hypothesis we came up with, we are fitting these values into that hypothesis, right? And trying to see how far are we, right? So what
Mm-hmm.
we are doing is we are summing up all these values, right? For each of
Mm-hmm.
the rows. So how many such terms will be there? M.
We
Yeah,
mm,
and
yeah.
therefore the average of these will be how much?
Those much divided by M.
Perfect, right? M.
Uh,
Okay, so now when you differentiate E with respect to, say, W1,
mm-hmm.
um, or let me just take one equation at a time. If you differentiate this error, okay,
Mm-hmm.
I'll just express it again. I hope that doesn't look ugly. So, so this was our y predicted, and this was w naught plus w1 x1 plus
Mm-hmm.
w2 x2. Again, it started doing that. I think when it heats up, then it goes crazy. When it heats up, the this app goes crazy, and I'm not able to draw it. I never knew why it happens.
Mm-hmm.
Okay, now here you see this. Now, what will be the rate of change? Okay, let me put it this way. Now, when we are saying error, we're talking about error with respect to first record. Okay, the error
Mm-hmm.
with respect to first record will be the whatever is the y predicted minus the y actual
Mm-hmm.
square. Now, question to you is, what is the rate of change of E with respect to the W naught?
We uh, I don't know. We make a one small change, like add like point oh one, uh, and we see the difference.
Yeah. Okay. So here we go. Right.
Mm-hmm.
You see this? We are just expressing this Y as this. Okay.
Mm-hmm.
And this one. Okay. Now, when we differentiate things, what happens is, what is the differentiation of x squared?
2x.
2x, right?
Mm-hmm.
And what is the difference? What is the if you differentiate, let's say, x, so x into 5 minus 1 square. What
Uh, That would be
5x minus 1, yeah,
yeah, 2x.
2 of
Uh,
x minus 5,
yeah,
right?
yeah,
So
right.
first of all, we differentiate just like this. Then we differentiate the internal part, right? The chain rule. Then we get 5 out of it. Correct?
Mm-hmm. Mm-hmm.
So it's like this. So first, whatever the way we did this,
Mm-hmm.
right? So
Mm-hmm.
x is square 2x. So x 5x minus 1 square is 2 of 5x minus 1. Correct?
Mm-hmm. Correct.
Till- And then inside when we are differentiating. So what is the differentiation of 5x? 5, right?
Yeah, 5.
Perfect. So here we are doing the same thing. So basically this weight is coming out, right?
Mm-hmm.
So when we differentiate this with respect to W naught, what's happening? We'll get the twice of this value, whatever is there in the brackets, right?
Mm-hmm.
W naught plus W1 x plus W2 x2
Right.
minus y. And
Mm-hmm.
since we differentiate, it doesn't have a coefficient, though it'll be like this, correct? So
Yeah.
twice of this when we are differentiating with respect to W naught,
Mm-hmm.
right?
Right.
If we differentiate it with respect to W1, what will happen? We will get
It'll,
twice of the same thing, right? Uh,
yeah.
let let me just write it quickly like this, so it becomes easier, right? Twice of whatever it was, right? Multiplied by what? Multiplied by x,
X. Right.
because we are differentiating with respect to W.
Mm-hmm. Yeah.
We are not
X1.
differentiating with respect to, yes, x1,
Mm-hmm.
right? So if you see that all of these values, when you differentiate them with respect to x, you'll get lots of such values, right?
Mm-hmm.
And that's what we have mentioned it there. So when you compute the mean, what will happen is we'll sum up all these values and m will come below it. So 2 by m, wx minus w multiplied by x. Okay, the only difference is when you do it on the matrix level, the x comes before and it becomes xt. Got it?
Mm. Okay.
Okay, so when we compute mean of all of these values, so what we're going to do is for for every row, we are going to, for every time, what we're going to do is we are going to find out the mean square error with respect to each of the gradient of W naught and so on. Got it? No, I'll just go back to, could you just show the screen? I think that'll make sense. Ah,
Sure. So, mm,
that
2M
side,
on that side, the
that side.
one,
Yeah.
oh, the one, yeah, the one I was looking at. So, yeah, so 2xt is basically the differentiate.
I can't see.
Oh, you can. Oh, wait, I didn't click on share screen. There we go. Okay. So now, so on this equation,
Yeah.
um, so on the right hand side, it is the
Yeah.
derivative of
Yeah.
um,
So that's what
h.
is happening. So this
Yeah,
mean square error is that one, okay, all over the instances, and we have basically concisely written it like this: X is a
I
big
see.
matrix, X is a big matrix, and this Y is an array of values, right?
I see. I see.
And the way you can think of it
Is
quickly
it
is,
possible?
yeah,
Mhm. Yeah.
okay,
Um. Yeah, I think. Yeah, I think it kind of makes sense. It's just I was wondering if you can send me the recording just in case I want to review, and in case I forget.
this current recording.
Yeah. Yeah.
Okay,
Easily.
okay. Yeah, I'll be
Okay.
sharing it with you. All right.
Sweet.
Now,
Thank you.
or you can have let's show you the screen. Okay.
Mm-hmm.
Once more, I'll just try to build the hunch again, because basically saying in a nice way that okay, we know y is equals to w dot x, right?
Mm-hmm.
Uh, 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 okay. Let me again. Missed that exact. I want to write exactly. Can you share once more? I'll just,
Sure.
otherwise I'll pull the,
There you
okay.
go.
So if think of it this way, y predicted is x dot theta. Okay. So let me first write it, then y predicted is x dot theta. Okay. And yeah. Okay. Now I can share the screen. That'll make more sense to you. Okay. In so all right, perfect. So we agree that y this is how we expressed, right? X,
Mm-hmm.
notice that if we are expressing that y predicted is equals to x dot theta, it has
Yep.
one extra one, right? One column extra one,
Mm-hmm.
all right? Like this one. So when we were saying y equals to w, right?
Mm-hmm.
So this xb is what we're talking right now, and this w is theta right now, okay? So,
Mm-hmm.
so y is equals to x multiplied by weights.
Okay.
And this x include one extra one to take care of this particular term, okay?
Mm-hmm. I see.
So this is our y predicted value. This is our kind of this theta is our hypothesis that okay, if we multiply our x with thetas, we'll get some y, right? Now, when we say like mean error, right? Mean error. What is mean error? MSE, mean squared error. So what's going to be? It's going to be summation of all the values, right?
Mm-hmm.
Divided by m. So it's
Mm-hmm.
going to be y predicted minus y actual for all the records divided by m,
Mm-hmm.
right? We put sigma over here
Mm-hmm.
just to represent that it's a summation that we first computed the y from first record and second record and so on. Now,
Mm-hmm.
this is the mean squared error. Now, what is the rate of change, or let me just put it this way, mean squared error is x dot theta minus actual y square divided by m, right?
Mm.
I'm just messing it up. Okay,
Oh yeah, yeah, yeah.
so here till this point you're clear, right?
Mm-hmm. Yeah.
And then when I say rate of change of MSC with respect to theta is how much? 2 will come down.
Yeah. It will come down. And,
2 will come down. It'll be like x theta
mm-hmm.
minus y multiplied by say x, because theta's coefficient is x. Notice that we
Right.
are differentiating with them, and it'll
Yep.
be by m.
Yep.
Okay. Now,
Mm-hmm.
since all of these values are in matrix and arrays, these values are in array, and therefore this same expression is slightly different when we do it in array using a matrix. So it'll become
Mm-hmm.
like twice of m. This x will be like xt. X is transpose, like we made it vertical rather than horizontal, and then
Oh, okay. So basically, you what do you call it?
transform it.
Transfer X
Yeah,
because X matrix multiplication is
we just rotated it.
rotated. Okay, I see.
So that's it.
Hmm. I
Okay,
see.
so this is how roughly you can make the hunch. Otherwise, if I have to go through the entire matrix, it'll be
Of
like
course.
I'll be able to do exact like why this is X transform, right?
Mhm.
And so on. Okay, so
Okay.
that's
Cool.
how.
Cool. Cool. Thanks. Thanks.
Okay,
It's a lot clearer now. Yeah.
all
Great.
right, all right. Go ahead.
Thank you. Okay. And the next equation is basically just um,
Are
the
you sure?
derived from the. Oh, sorry, I didn't share the screen. Uh, Here you go. So the next equation here is just derived from this equation above.
Yeah.
Next theta is what is this little thing like this
This is some number.
sum number? Oh,
Yeah.
okay.
Yeah. Okay. We'll
Oh, I
just
see.
we call it learning rate, and
Learning rate.
we when we are training our algorithms, what we do is we try many values of eta
Mm-hmm.
and see which one is working best. Okay,
Mm-hmm.
this is called the learning rate. Okay,
Okay.
so and this is our one learning steps. Okay, so what we are trying to do here is that we are what we are doing is for every thetas, right? What we do is for every theta we tweak it a little bit. This
Mm-hmm.
equation actually, theta is a array of values here. Okay,
Mm-hmm.
we are essentially writing a for loop here saying for every theta this is what we are going to do. Okay,
Mm-hmm.
first what we're going to do is for every record, for every theta we are going to compute the rate of change of error, right? Rate of change of error. So this is our gradient of error. So
Mm-hmm.
now imagine this MSE is an array of values. Okay,
Mm-hmm.
and I'll just put it another way. Let me put it this way. So we are saying theta naught equals theta naught previous minus minus eta multiplied by rate of change of error with respect to theta naught. Okay, let me now share my screen. I think it'll make sense to you. Okay, did I understand your question correctly?
Okay, so theta naught
Theta
is
naught is theta previous value. This is the previous step value.
mm-hmm.
Okay. And eta, this is eta multiplied by rate of change of error with respect to theta naught. Okay.
Mm-hmm.
Similarly, we'll have theta 1 equals theta 1's previous value minus eta multiplied by rate of change of error, overall error,
Mm-hmm.
divided by theta 1.
Okay,
Okay, I'll
so
just inform my team that I may not be. Okay, just give me a second. In one on one. Okay,
okay,
now this is clear, right? So
yeah.
what we did was we assumed the initial theta naught,
Mm-hmm.
computed the rate of change of error with respect to the theta naught.
Mm-hmm.
Now we are saying that theta naught's new value is previous minus rate of change of error with respect to this. Why are we doing minus? Because if this rate error
Mm-hmm.
was increasing,
Mm-hmm.
we'll have to decrease theta. Okay,
Mm-hmm. Mm-hmm.
meaning think of it this way: if we are like, let's plot this error,
Mm-hmm.
and this is our theta, right? If
Mm-hmm.
let's say we are assuming the curve like this because it's
Mm-hmm.
squared, mean squared, so the curve is going to be like this. It's a
Mm-hmm.
square. Now we're saying that at this value of theta naught, is the error increasing or decreasing? Yes.
The
Slope is going to be like this, right?
yeah,
So the error is going to decrease at this point. Or what is the gradient value at this point? Negative or positive?
uh,
On increase of theta, what is this? Is it going to increase or decrease?
it will decrease.
Decrease, right? Therefore, it'll be negative, right?
Yeah.
And in case of negative, which direction do you want to go to? That side? You want to decrease theta or you want to increase theta now in the next step?
I want to increase it.
Increase it, right?
Mm-hmm.
Therefore, we are putting a negative sign. We are saying that if this thing
Mm-hmm.
comes out negative, we
Mm-hmm.
will subtract it. Okay.
I see.
So
Okay,
it's
makes sense.
now
Okay, I see.
now that theta increased. Now similarly, imagine that we were here,
Mm-hmm.
right?
Mm-hmm.
And the rate of change, this proportion will be positive and negative.
It'll be positive, so we if you decrease it.
Yeah. So since we have two things, so here or here. So since it's positive, therefore it'll be negative, right? So
Mm-hmm.
and then therefore it'll theta will increase,
I
decrease.
see. I
Okay,
see.
so that's how it is.
Okay, I understand now. Thank you so much.
Okay,
Thank you.
now to write, like, there will be, say, if you have X number of columns, right?
Mm-hmm.
N number of columns, there'll be N plus one such statements, correct?
Mm-hmm.
Theta naught, theta one, theta two, up to theta N, correct?
Mm-hmm.
So
Yep.
there'll be, this one is extra. So instead of writing them like so many equation and plus one equations, what we do is we write them like an array. Okay.
Mm-hmm.
Imagine that we put it something like this: theta naught, theta one, and then we say theta naught previous. It's like, I don't know
Mm-hmm.
why
So not, yeah.
when it's not even writing.
It's okay. I
Okay.
heard you.
So, so oh man, I think I need a better program. Theta naught, theta one,
Mm-hmm.
okay, theta two equals theta naught previous, right?
Mm-hmm.
And theta one previous,
Mm-hmm.
like that.
Mm-hmm.
This is theta naught, okay,
Mm-hmm.
like that. And theta two,
Mm-hmm.
we can write the same thing like in a matrix format. So instead of saying that we are writing a for loop, we are
Mm-hmm.
saying that it looks like we have,
So it's
okay,
like a matrix. So
yeah,
matrix computation is
yeah,
basically a way to simplify a lot of simple
yeah,
algebra. I
yes.
see. I see.
So
Now it all makes sense.
it's
Mm-hmm.
like array operations actually. Okay. Now the same thing we can nicely say in clean manner, saying
Mm-hmm.
all the thetas are going to be previous thetas minus eta multiplied by their rate of change. Got it? So this is a vector. This is a vector now, which is
Mm-hmm.
representing an array of values. This is another vector, and
Mm-hmm.
this is another vector. That's what is happening in your case.
Mm, I see.
All right.
Now I understand. Okay, cool, cool. Now I understand the second equation now. Awesome.
Okay.
Okay, so that was just an aggregation, um, and theta is a vector, and vector minus that's aggregation of that. Okay,
Yeah.
got it. Sweet. Okay, now it comes to my last question. Um, so you told us that we might get into a local medium with
Hmm.
a gradient descent approach.
Hmm.
So I imagine if we just throw in a few more random points and do the same uh, technique, gradient descent, and it's gonna reduce the chance of getting into a local medium because we throw out so many random things. So the more test case we have,
Hmm.
the more likely we won't get into the the local medium, right?
Yeah. Come again. So
Oh yeah, so let's say we're trying to use gradient descent approach to find out a certain value, but there's a good chance that we get stuck in the local medium,
yeah.
right? But if we choose a different, so the initial value is a guess. If we choose different guesses,
Yeah.
if we choose a bunch of random guesses, it's
Yeah.
the more we have, the more likely we will avoid the local minimum.
The
Yeah,
stock. You are talking about stochastic gradient descent.
so I'm talking about because to avoid to reduce the chance of getting stuck in
Yeah.
a
Yeah.
minimum, a local minimum.
Yeah.
Do we just throw in more point?
So one way would be that we um, so imagine for a moment. So I'll just draw some more things, and then
Mm-hmm,
that should make sense. Okay.
mm-hmm, mm-hmm,
So in case of gradient descent, the challenge is that imagine that here our error was not like the way we thought. Okay.
mm-hmm, mm-hmm.
Okay. These are our thetas, or you can say weights, and the error seems to be something like this.
Yeah,
Okay.
like a W. Yeah, so you have it.
So if our initialization of theta, like let's say the way we were initializing, the theta ends up here.
Mm-hmm,
Okay. the
Mhm.
theta ends up here. Like that's, we did a randomization. Theta
Mhm.
ends up here. We got theta here, right?
Mhm.
So we will end up in the local minima,
Right.
right?
Mhm.
Now, if theta was found, first initial assumption of theta was here, we'll
Yep.
reach the
The actual
actual,
minimum.
right? So there are two things. One, what people do is, what they do is they basically, when they run the gradient descent multiple times with the different initializations of theta,
Mhm.
right? That generally also gives a different, that also gives a different outcome, right?
Mhm.
Now, the other thing is that we do is, if we have like lots of data points in our
Mhm.
table, right?
Mhm.
So right now we computed the mean squared error for all of this. So we did an assumption of theta, right?
Mhm.
We like this theta is going to be theta previous, right?
Mhm.
This is our previous minus the, let's call it, rate of change of error with respect to the theta. Correct? This is okay.
Yep.
Ignore this one here. Okay.
Mhm.
So theta equals to theta previous multiplied by some
Mhm.
constant called eta. Just, this is a constant.
Mhm.
Okay, I'll describe what it means again. So if this is too much, what will happen is we'll keep on jumping to too
Right.
much. If this is too small, we'll go slow, slow step. It's basically, it describe kind of learning rate. How
Mhm.
fast do we want to converge, or how fast we want to?
Mhm.
If this tiny, the impact on every time is going to be tiny. If this is
Mhm.
huge, the chances that we will become, it might never converge.
Right.
Okay.
Mhm.
So, perfect. So this is what it is. So what we did was we assumed thetas, correct? We took some assumption of thetas
Mhm.
and computed on this record the actual value of the predicted value of y. Then did the same thing on all the rows, correct?
Mhm. Mhm.
Okay. So what we did was or you can say that instead of computing the actual values, we computed the rate of change of error. Okay. On all the records, we took some assumption of theta. Based on that, we computed this factor. Okay.
Mhm.
This is not computed. This is fixed all across, right?
Mhm.
So we started somewhere random. And then what we did was, in case of the batch gradient descent we talked about is, in which the usual one, the one that we just talked about, is called batch, because what we do is we take an assumption of theta,
Mhm.
go over all the data points, compute all the rates of change of error, and then
Mhm.
take an average of that, right? We
Mhm.
computed mean square error on all the records, correct?
Mhm. Mhm.
So in that case, what happens is the chance of us staying in the local minima is very high. It has been observed. Okay.
Mhm.
So
Mhm.
in these cases, we might get stuck in the local minima. So what we do generally is, that we for the first time, instead of going all over the records, finding the average value of rate of change all over the records, what we do is we try only one record at a time.
Mhm.
We try one record, then another, and so on. Because of
Mhm.
which, what happens is this guy jumps a lot. Okay.
Mhm.
As per the opinion of one person, one instance, your rate of error should increase, while as per the another one, it should decrease. And because of that, it kind of jumps out of the local minimas. So it has been
Mhm.
observed that the SGD, this is called a stochastic gradient. Instead of computing on every step, instead of computing the average of all the rate of changes, all the gradients, what we do is we compute, in case of gradient descent, we compute only a gradient descent with respect to one single record, right? So this actually is a little crazy and it runs around a lot. Imagine we have two thetas, okay? For now,
Mhm.
let's say theta 1 and theta 2, okay?
Mhm.
And we are representing the overall error like the depth of this circle. Imagine this is like a bowl, okay?
Mhm.
This is like a bowl, I'm just trying to draw a nice bowl. Okay. And this is the point where it's the deepest point of this bowl. You're looking at the bowl from the top. Okay.
Mm-hmm.
So this is your theta 1 and this is your theta 2. Imagine for time being, right?
Mm-hmm.
So your purpose would be to reach to that lowest point in this bowl. This bowl represents the depth of the bowl is representing the error,
Mm.
correct?
Yeah.
Now, imagine that this bowl had I'll talk about the multiple minimums later. Like for example, I'll give the same example what I did just now. So if you think about a gradient descent, what you will do initially, you will choose some theta naught and theta 1 and theta 2, some values of thetas. We randomized it, right?
Mm-hmm. Mm-hmm.
And from here, we computed the slope, meaning rate of change of error with each of thetas, right?
Mm-hmm.
So ideally, you will just keep on going like this. At every step, you will basically keep on going like this. Got it? No? No?
So,
Okay, let me rephrase the question. I think this is not clear.
mm, so like in reality, the bowl is not like a perfect bowl. The bowl is like a really weird shape. It has like a bunch of local minimum,
Yeah,
which are kind of like the holes, like what do you call it? The dent, the
yeah,
denta on the bowl. So
yeah.
we,
There could be like many depths, like some dent in the bowl, right? In case of multiple local minimas,
mhm,
correct?
yeah,
So yes, I'll come back to that. But this bowl is clear, right? So we start here at theta 1 and theta 2, and we keep
yep,
on going down the bowl, right?
mhm, yep,
Now, this is a case of the situation where we are doing mean square error, okay? It's actually very nicely going down. Okay,
mhm,
reason is that since we are taking average, so we are going happily in that direction, right?
mhm, yep,
Now, when we take opinion of only one instance and compute the rate of change, okay,
mhm,
what happens is it goes like this gradient descent goes really crazy. Okay, it goes like this, like this,
mhm,
like this,
mhm,
like this. Okay, and it might actually jump out of it also, and like
mhm,
this here, like this, and like here, and then might take a long time because instead of computing the average of all errors,
mhm,
we are just taking the error rate of the gradient of error from any random instance.
mhm,
So this is stochastic gradient descent could be really crazy. It might go like this. But good
mhm,
part about stochastic gradient descent is that it will jump out of local minima.
mhm,
Okay. So in case it gets stuck in the local minima, what it'll do is imagine if you look at from the other side, if there was this local minima. Okay. So we started
mhm,
here. Okay. Suddenly it'll say, okay, go down to like the rate of change we are here, okay?
mhm, mhm,
And when we consulted the gradient, what happened was that we found that rate of change is just too much, okay? The rate of change came out really high, okay?
mhm,
And let's say we ended up suddenly here
mhm,
because of gradient descent,
mhm,
stochastic gradient. Then again, so the chances of jumping from here to here is high when we are using stochastic gradient descent.
mhm.
All
Okay,
right.
okay.
So this error curve will be different for different instances, and the bowl that you see right now, this nice bowl, is basically the average of all the bowls. Okay,
Mhm,
because the if you just plot the bowl with respect to only one instance in your record, you will get the bowl, right?
mhm,
You'll get the bowl for even one instance, like for every value of theta, we plotted this.
mhm,
Now we, for every instance, the error is there. For every instance, we can compute error, right? For every row, for every record.
mhm,
For every record, we can compute the error. And that's why there are, if you have m instances, there are actually M balls. Okay,
Mm-hmm. Yeah.
they're actually M balls, and therefore, as per one ball, this point is here in the local minima. As per another, this point is not in the local minima. Okay,
Mm-hmm.
and that's why
Okay.
it jumps a lot. And though stochastic gradient takes long time to converge,
Mm-hmm.
it has, but it does not get. Generally, it gets out of.
Local
Generally,
medium. Mm-hmm.
it gets out of the local minima, the local dent in the world.
I see. I see.
Do I make sense?
Yeah, it makes sense. Cool. Thanks. How do you? So the second approach, I remember there was a name you typed, but I forgot. How do you spell the second approach?
Yeah. I'll just. Okay, let me share the screen again, and I'm talking about the stochastic.
Stochastic.
Okay, stochastic, stochastic gradient.
Uh, okay, got it.
All right.
Oh, okay. So stochastic is like it's random. Okay, got it. Mm.
So we just yeah. Basically, the probabilistically random things are called stochastic. So yeah, probably
Cool,
my
cool, cool.
pronunciation is not that clear.
Oh, no, no, it's not your pronunciation. Your pronunciation is good. It's just I don't know this English word. I speak
Okay.
English as it's my second language.
Okay. Where
Don't
are
have
you?
it.
Where are you
Yeah.
from, Leo?
Oh, I'm from China.
Oh, nice.
Okay.
And how's it in China?
China. I have China. Actually, I was from China, but I have left China for like 12 years. I've been staying in Canada for 12 years.
I see. I see.
Yeah, I finished my high school there.
I see.
Cool. Cool. That's all my questions. Thank you so much, Sandeep.
Uh,
You're
all
so
right.
helpful. Yeah.
Great. Great. Wonderful.
Mhm.
So, what do? You are working somewhere? You are.
Yeah, I'm a web developer at a call center software company.
Okay.
I've been I have been a developer for 5 years.
I see. I see.
Hmm.
Okay. Wonderful. So you are good with front end, back end, and all.
Yeah, I do both front end and back end,
And the
but I
back
haven't
end.
done nothing about I haven't done anything about machine learning. I want to learn
Okay.
machine learning knowledge so that I
Okay.
can proceed on
Okay.
my goal.
Okay.
Sweet.
This is good. This is good. So I'm thinking that we should do a end-to-end project, as in extreme end-to-end project. Okay.
Hmm.
So let's say imagine somebody's running a PHP website, right?
Hmm.
Or somebody's running what do? You Django or what?
We sorry,
The
what do you mean?
the backend? Do you what
Yeah, I
frameworks?
do backend. Yeah.
What frameworks do you use?
What framework? We actually don't really have a specific framework. We kind of have our own framework.
Okay.
The founder of the company wrote his own framework.
What
The
what, la-
only
what language is that?
it's using PHP. All the backend code is in
Okay,
PHP.
okay, okay, that's perfect. So imagine that we have to build, let's say, amnist example, right? The
Mm.
amnist example where you have to guess the digits. Imagine we have to build a web app that when people draw something, it predicts that this is that digit. Okay.
Hmm.
So I want to do that extreme example because the truth is that eventually, I mean, all of us would have to learn machine learning. Uh,
Hmm.
I mean, I am a very passionate um, web developer.
Hmm.
So I actually wrote the framework previously in my previous startup for the
Cool.
whole thing. And I've written, I started my career. Can you believe that I wrote my first web application in C++?
Oh, really? Wow, that must be really hard.
Yes, yes. So the frameworks were not there till that point of time. I wrote my first web app in 2000, uh, 2000, year 2000.
2000. Wow, that's
Okay.
even a lot better than my boss.
Okay. So yeah, basically that time we wrote like first one in C++. Second app was in shell programming, the back.
Oh, shell programming. Wow, crazy.
Then Perl, then Java, then JSP, and then Python, then PHP, and yeah, those are the things I did. Now,
Wow.
good. So I'm thinking is my idea is that we should build a end-to-end web app
Mm-hmm.
whereby there is a machine learning component,
Mm-hmm.
and uh, and then how to use that machine learning component in your app, in your web app. That'll be
Mm-hmm.
really cool. So I'm thinking of that way, that to build a thrift service and then let your PHP code call the thrift service and then display it. The PHP part, the web developer part will be tiny, okay?
Mm-hmm.
But what I'm seeing is that I think there are only few. It's very not many people know. There are people who are into web development, but they don't know anything about machine learning. But
Mm-hmm.
in a industry, in the industry, a person who doesn't know web development, they can't really do much. I mean, I have seen three cases, for example. Amazon, you may also like it. You may also like that. Those widgets are there, right? That was my page.
Mm-hmm.
So there was machine learning engine that we had, and then we were using in the web. So it's a good opportunity to build an end-to-end project, and then you will get the full hang of it. So all your knowledge will basically be strengthened with the machine learning part, and that's something wonderful.
Cool.
Okay, because pure machine learning people don't like people. If I have to hire a machine learning engineer, if they don't know web development, I would not hire them.
Mm-hmm.
Honestly,
Cool.
I mean, at Amazon, all the hiring I did, um, if there was a person who was first a web developer and
Mm-hmm.
then learned machine learning, we would hire him. Otherwise, we won't. Even for
Oh,
machine
that's
learning. Yeah,
that's great.
yeah, yeah,
I have some advantage here.
yeah. All right. So you are doing a very right thing. All
Great.
right.
Great. Awesome.
Great. And do you mind if I make it public to the class or others, this video?
Sure.
I think
No,
there's
no problem.
nothing
Of
public.
course. No
All
problem.
right.
Mm-hmm.
All right. Wonderful, Leo. I hope these classes are useful to you. And
Yep. Cool. Thanks.
all right.
Yeah, it is. Thank you so much, Sandeep. Have a good day. I'll see you on our time Friday and your time Saturday.
Okay. Bye.
Okay, sweet. Thank you.